एंड पार्टिसिपेंट ये 2:30 बजे हम शुरू कर रहे हैं. दिस सेशन विल बी 90 मिनट्स एंड आफ्टर दैट जो क्वेश्चन होंगे 10 to 15 मिनट्स जो है आप यू कैन आस्क क्वेश्चंस फ्रॉम देयर इन दैट केस. और मेरी एक रिक्वेस्ट रहेगी कि जो कल हमने क्वेश्चन पेपर आप लोगों ने दिया है, एग्जाम दिया था, उसमें यदि आपका कोई कंफ्यूजन हो तो दैट यू विल श्योरली क्लैरिफाई फ्रॉम पटकी साहब. यदि किसी का आंसर आपको नहीं आ रहा है या फिर जो डिस्कशंस हुए हैं उसमें आपको अभी भी क्लियर नहीं है उन क्वेश्चंस के आंसर, तो काइंडली पटकी साहब के साथ उन क्वेश्चंस के भी डिस्कस कर लें, क्योंकि सेकंड सेशन के बाद कल के बाद हमने फिर से एग्जाम लेना है और मोस्टली उसमें क्वेश्चंस रहेंगे. वो मोस्ट ऑफ दैट क्वेश्चंस विल बी इन दैट क्वेश्चन आल्सो. तो काइंडली उसको भी आप लोग क्लैरिफाई करके डिस्कशन कर लें पटकी साहब के साथ. थैंक यू.
Yes. So now this session we'll discuss the protection performance, various grid contingencies and disturbances, and how protection will perform, and what are the protection requirements. Protection as well as controls. We have seen that basically on the generation power station side, it's a AVR, the governor, power system stabilizers. These are the primary generator controls. On the transmission side, again, for voltage control, by way of reactors, capacitors, SPCs, HVDC lines, FACTS control. These are the control mechanism on transmission side. And then secondary and tertiary control for the purpose of managing the frequency and the loading on various circuits. So then we also talk about special protection scheme and islanding schemes, etc. And during and the black start operation, and during this islanded operation or black start operation and special protection scheme, again, what are the preventive controls which are available, and what sort of mitigations can be provided. Again, they are listed here. I will not repeat because we have already discussed in detail. On the disturbances and mitigation measures, there is a lot of literature is available. There are SIGRE reports are available, and protection manual of CBIP also dealt with some of the issues arising out of 2012 grid collapse. What should be the philosophy for protection as well as settings. Dealing with issues like voltage stability, transient and frequency instability. Voltage instability related protection aspect which was encountered during 2012 grid collapse was basically the load encroachment phenomena and operation of zone 3 due to overloading of the lines. Transient and frequency instability resulted into trippings of line on power swing, and also tripping of generators due to under frequency conditions. So both these are very relevant. And then there was, of course, cascade tripping of lines due to successive overloading one after another. Also, the reactive power flows resulting into the excessive voltage drop at the receiving end of the transmission lines. Reference is given here. If any one of you have access to SIGRE, this is the working group 3409 who have published this report. It's a good reference document for reference. Some of these reports are, even if you are not a SIGRE member, they can be accessed free of charge. Since the report is more than 3-year old, it is available free of charge. We'll just revise some of the concepts. When we talk about voltage stability, it's the ability of the system to maintain voltage so that when the load admittance is increased, load power will increase such that both power and voltage are controllable. Instability occurs when the heavy system loading creates large reactive power demand that results in excessive voltage gradient between generating source and the load centers. And we have seen some of the load versus voltage curves with a typical that nose shaped curve where the voltage collapse phenomena occurs after a particular point and then the total collapse takes place. Some of the actions which are required is blocking the operation of transformer on-load tap changer. When the reactive power flow increases due to voltage drop phenomena, if the OLTC operates at this time to boost the voltage, actually it becomes counterproductive because then more power will be drawn as you boost the voltage, and then again the power factor will be poor and it will further lead to the collapse. So on the load center side, when there is a overload situation on the transmission line, the load center side transformers, you should block the operation of the on-load tap changer. Switching of the capacitor bank, static var compensators, wherever there are margins are available, the corrective actions can be done either manually or automatically. In certain cases, under voltage load shedding scheme is suggested in order to prevent voltage collapse due to excessive reactive power. Basically, because of the behavior of the motive load which is there. This is the curve which we were talking about, where this is the sending end voltage, this is the receiving end voltage, and you can see as the line loading, this is the real active power loading increases, this is a voltage drop, and the reactive power flow will increase, and beyond this point, voltage will collapse dramatically because of the behavior of the motive load again. Because the reactive power drawn is proportional to square of the voltage. The load side, the current and reactive power drawn will sort of lead to voltage getting lower and lower. So it's like a vicious circle. So there is a more voltage drop, so more reactive power is drawn by the loads. So more drop takes place. So further there will be then more reactive power drawn, and finally the collapse takes place. There is a point where you can say the active power becomes so less and voltage becomes so low. So mainly load is drawing only the reactive power. Okay. The transient stability we had already discussed. One of the phenomena of transient instability which we have not discussed is the out of step operation of the generator, or you can, power swing experienced by the lines. So power swing experienced by the line, or if that is not controlled, then the generator will experience pole slip phenomena, which is out of step behavior. It's a loss of synchronism basically, and if this further is not controlled, and the system separation will occur. So that is the sort of consequential sequence of the collapse subsequent to transient instability. Once this power swing phenomena takes place, then as we experience in various disturbances in India, the cascade tripping takes place because some distance protection will respond to power swing or the voltage collapse phenomena. Voltage collapse phenomena is basically resulting into low voltage accompanied by very high current, which is mainly reactive current. And this low voltage and high current will result into encroachment into the impedance setting of the distance relay, mainly zone 3, which is very close to the load point of the line. Longer lines are more susceptible to such a phenomena. So long 400 kV lines, we need to ensure that during the dynamic condition when such a overload occurs, the lines do not trip due to distance protection. Because if one line trips, the loading will get diverted to parallel line. The parallel line will also then trip, and this cascading effect will continue on other corridors which are in parallel. So this is an important aspect as far as the grid collapse prevention is concerned, how to prevent cascade tripping. Which are the protections which play a role? Primarily distance protection. When the system overcurrent and overload protection. Overcurrent and overload protection, many times what happens is this: if the settings of overcurrent protection are not very well coordinated, the overload condition during the system disturbance due to voltage instability can result in overcurrent relay to operate in an undesirable manner. This is the same reason actually was a cause of one of the recent disturbance in the western region when even the Bombay was affected with a power shutdown. There is a tendency by some of the utilities to really mix up overload protection with the overcurrent protection. One aspect which has to be remembered is overcurrent protection on the transmission line is a backup protection to distance relay for fault protection. So it's a protection against the short circuit faults, phase to phase or phase to ground faults. Whereas overload phenomena is basically a three-phase phenomena. It's not a fault condition. So the phase overload relay setting should not be such that short time overload should not result into phase overload relay operation. So one of the recommendations for the application of line protection is you should have main 1, main 2, both protection to be distance relays, and overcurrent protection as a backup should be provided only for earth fault. Phase overcurrent protection is actually not to be provided for 400 kV lines. Some of also critical 220 kV lines, which can trip in an undesirable fashion. Similarly, generator current limiters, stator current limiters, over-excitation limiters, under-excitation limiters, and those settings to be and other protection schemes, so that the limiters provided in the AVR should act as a first line of defense before the protection is called upon to operate. That is basically the coordination between the excitation system limiters with respect to the protective relays. Are you able to hear me? I am getting a signal of bad network quality. Can you hear me?
Yes, sir. Your voice is perfectly clear.
Yes, sir. We are able to hear.
Yes,
Okay.
sir.
Yeah, there was an error message saying the bad network quality. So, okay. Another protection which can malfunction if not properly coordinated is under voltage protection. This under voltage protection is primarily at the thermal power stations where the big auxiliaries, ID fan, FD fan, boiler feed pump, etc. They are all protected with under voltage protection. And this under voltage protection on the induction motors should be set in such a manner that the grid disturbance either during fault condition, that means if there's a single phase to ground fault and voltage dip is there, this under voltage protection should not operate. For a single phase to ground or double phase to ground fault, it should be operating only on three phase under voltage condition. Now the setting of the under voltage protection should be such that the grid disturbances and the mitigation measure in terms of special protection scheme, reactive power support interventions, and other schemes should get a chance to correct the voltage. Otherwise, if the power station is trips on under voltage of the auxiliaries, then it will further aggravate the situation. So that care has to be taken while setting the under voltage protection in the thermal power stations. I gave you as an illustration the example of 2012 grid collapse. This is what was the summary. Basically, there was a loss of 400 kV Bina Gwalior line. This is a basically line which was interconnection between western region and the northern region. And this line operated on zone 3 of the distance relay due to overdrawal, and this resulted into separation from northern region and western region. This separation has basically occurred because there was a double contingency, N-2 contingency already, because one line was out for construction and then second line after tripping resulted into overload of the line, and load encroachment feature was not there at that time. So line tripped on zone 3 protection. Once this interconnection basically got snapped, then the load which was being supplied from western region to northern region, that flow got diverted towards eastern region back to the northern region via eastern region. From western to eastern and eastern to north region, this swing or power flow from western region to northern region to western region to eastern region to northern region, this basically swing has resulted into instability, and number of lines then tripped, and then there was a cascading effect, and this is what was really the root cause of complete grid collapse. As per the present protection practices,
तो ये कितने अमाउंट का बनता है? जैसे इसमें लिखा हुआ है कि अप टू 14 अक्टूबर 2020 4,80,000.
the power swing detection basically is used to block tripping in zone 2 and zone 3, but it is allowed to trip when the power swing locus passes through zone 1. Now, we'll explain this more in detail, but this has its own issues because in a severe instability, the possibility of power swing passing through zone 1 and further recovery then gets ruled out. It is allowed to trip in zone 1 with the assumption that if the power swing locus passes through zone 1, that means the instability is not recoverable. So it's a sort of a leading to system collapse. So the recent studies do indicate that this philosophy may not be a good philosophy for long-term reliability of the power system. So there was a revision suggested. Similarly, the damage to the generator, if the power swing is not arrested on the grid side, then the electrical center will move towards the generating plant. And in that case, if the pole slipping takes place, then it is then risky for the generating station. So the power swing detection, tripping has to be coordinated with the pole slip protection, and it should not happen that because we have blocked the tripping on power swing on the line, and the swing will move towards the generator and generator will trip. But otherwise, again, yeah, loss of generation will result into tripping of the collapse of the grid. We talked about the protection scheme based on overcurrent and impedance principle. Both have limitations during system disturbances. So the settings wise and the characteristic wise, again, there is a recommendation. Relay should be able to detect fault condition and distinguish it with the power swing type of situation, which is a disturbance event, but which can be recoverable. It is a recoverable swing. So the main challenge is how the protection relay, because protection relay will only see the impedance as it swings, and whether the swing is due to the fault, because when the fault takes place, that time also the impedance change is there, and the rate of change of impedance will be though different. During power swing, the rate of change of impedance will be different, and so this can be one of the criteria how the relay will distinguish between the power swing versus the fault. So this is basically one of the major protection review. How do we avoid distance relay tripping due to line overload during emergency loading? During the emergency loading, there will be high load currents with low voltage, and there could be power swings. So how this can be tripping can be prevented in such a contingency when the system disturbance is there. So that was the main sort of summary recommendation as far as protection is concerned. Now, now this type of system disturbances, they don't happen suddenly. The experience suggests that there is a first slow phase of the disturbance when the gradual voltage decline will start happening, and it may take minutes for this overload. As I said, that PV curve where that nose point to be reached, it will take some minutes because slowly, progressively, the voltage will start going down. More reactive power will drawn by the load. Again, voltage may further go down, and again, it's like a vicious circle. So this may happen gradually. So it's not that something which happens within seconds. So we should see what actions can be initiated when such a phenomena takes place. So there is a early warning system at the load dispatch centers, which will alert the system operator to take corrective action as the margin becomes smaller. That means the margin of stable operation for the voltage collapse. That means the on the PV curve, much before the nose point approaches. Nose point is like a knee point voltage of the magnetic core. So before the nose point operated, the corrective action, there is normally sufficient time to take corrective actions. And that is basically the role of system operator. When the early warning alert is provided for the critical system behavior. In the recent 2020 grid code, it has been mentioned that the system will be classified into 3 categories. That means when it is early warning of the impending disturbance, then the alert situation, and third is the disturbed condition due to this thing. So the system behavior is categorized into 3 categories, and special protection schemes and the manual intervention then can be coordinated accordingly. We already talked about what can be those mitigation actions. It is switching in of the shunt capacitor banks or static power compensator or STATCOMs or load shedding schemes. The generating stations can reduce active power within the capability curve so that more reactive power can be supported at that time. Action is at the transmission level as well as at the generating station level, so that the reactive power resources can be maximized. Similarly, the role of on-load tap changers at the appropriate load centers so that voltage can be maintained before it leads to overload situation. Load shedding schemes we have already discussed, but this need to be again not an under frequency based load shedding scheme, but basically to avoid the overloading situation which can lead to the voltage collapse. This is where the under voltage based load shedding schemes might be helpful, which at the moment in India we are not really deployed under voltage based load shedding scheme. Auto reclosure as a measure for maintaining transient stability. We had discussed briefly yesterday also. Basically, if you see electrical fault, we had this 2 machine model of the power system where there is a machine 1 and machine 2, and there is a interconnecting network, transmission network, which is represented by transmission line X and R. And when the fault takes place, basically what we have to do is this: immediately after the fault, the difference between the turbine power and electrical power, mechanical prime mover power, electrical power, this difference should be minimized. And this can be minimized by ensuring that this electrical power, active power component doesn't come down drastically. And this is achieved through single pole tripping and single pole auto reclosing. By keeping two poles intact of the line, you allow active power flow on those two, and one phase which is open, the parallel line will correspondingly take the load, so that system stability will remain intact. So this is basically the accelerating power, and this accelerating power can be minimized. Instead of 3-pole opening, you are opening only 1 pole for a fault, thereby maintaining the integrity of the network as much as possible. This is the actual real FDR record, fault disturbance record of power swing. You can see how this swing has, and then then on the swing here, the tripping has occurred. On the generating station side, during the grid conditions, there are different hazardous conditions. They are listed here. Over voltage, there can be rotor fault due to excessive induced when you operate the machine in a asynchronous manner. During power rotor, which can result into insulation failure of the rotor. There can be total loss of synchronism, under frequency, over frequency, overload conditions, unbalanced loading, loss of excitation, reverse power. All these are different types of situations which can be faced in disturbed condition, including black start operation. Various protections are against each hazard. The protections are listed here. You have to remember the different types of generator layout. This is one of the commonest, you can say, the layout of the generator. There is a generator, there is a auxiliary transformer for excitation, and then there is a station supply transformer, auxiliary UAT, and then there is a generator transformer connected to the grid. So all these protection schemes, we have to see that they maintain their integrity and no malfunction takes place during the grid disturbance. Most common protection which is susceptible to have uncoordinated operation is the backup protection on the generator, the impedance relays, and we'll see that important aspect is, again, during system fault condition, impedance relay are considered to be better suited compared to the overcurrent relays, because overcurrent relays have a problem of discrimination due to the asymmetrical nature of the fault current. This is, as we saw, the fault current has a heavy DC offset, and then gradually the fault current will come down to a steady state fault current value. So this is the sub-transient phase, this is the transient phase, and this is the steady state short circuit current. And this decremental nature of the fault current results into some of the generator backup protection schemes, especially the overcurrent protection scheme, not to recognize this as a fault current, because this current can sometimes approach very close to the actual load current. So one of the option is to go for voltage restrained overcurrent relay, so that overcurrent accompanied by under voltage, only that is taken as a fault, or go for the distance protection, which we talked about here. Now, what are the issues with the backup protection? In a generator, you have a generator, transformer, generator, and then there's a bus bar, and there are lines. The system backup protection is also provided as a overcurrent relay in the neutral of the HV side of the generator transformer. So you must have seen there is a inverse time or definite time earth fault overcurrent relay in the neutral of the HV side of the transformer. So the coordination of the earth fault overcurrent protection on the line and the backup protection, system backup protection on the generator neutral, this becomes an issue. Especially the inverse time coordination becomes sometimes very difficult to achieve, because the fault current seen by overcurrent relay on the line and the overcurrent relay here would be almost the same. Moreover, if there are a number of generators in parallel, then this neutral current due to system fault gets shared with all the generator transformers neutral. So this current sometimes may not be sufficiently sensitive. So in terms of the setting of this overcurrent relay, as well as the time coordination with the line protection is critical to maintain the proper coordination and avoid the undesirable tripping. Second is this impedance relay, which is acting as backup. This impedance relay has two stages. On one stage, it takes care of the phase-to-phase fault in the generator or the bus duct right up to transformer. At the typically hydropower plants, you will have generator transformer located at quite a distance from the generator. So this distance is sufficiently long, and this backup protection covers generator as well as this interconnection right up to generator transformer in its zone 1. Then the switchyard, which is and the outgoing lines falls in that. Any fault taking place either in the switchyard or on the outgoing transmission line also need to be covered as a backup protection on the impedance relay. So this impedance relay can reach up to say 50% of the shortest line which is there. So when the system disturbance takes place, there is also a risk that this impedance protection, which is zone 2 of that, which is reaching into this line, do not operate due to overloading or power swing condition. In the so when the power swing phenomena occurs, the impedance may move into the operating region of the zone 2 of the impedance relay, and that can cause malfunction. So again, this coordination becomes important. This is what is illustrated in this diagram. You can see that this is your generator zone of the impedance relay. Then there is a generator and the transmission line, and then there is a load point. So there is a safe margin kept between zone 2 reach of the backup impedance relay and the load point. so that this load doesn't encroach into this zone 2 of the generator protection during power swing or any system disturbance. So that is one of the main important aspect of coordination. If you see the capability curve, this is the generator capability curve, which we have shown. We have seen it yesterday also. This is the active power. This is MW axis. This is MVR axis. Normally, we are operating in this quadrant. Now, if this same capability curve, if you have to represent in terms of impedance diagram, that is R and X, then it will look somewhat like this, the impedance plot. Now, this impedance plot of the capability curve has to be carefully coordinated with the loss of excitation relay. Now, here we have drawn the impedance plot as per the capability curve. And you can see when you choose the loss of excitation protection of the generator, the loss of excitation protection is also based on the circular impedance characteristics. And there are two stages of loss of excitation. One with a smaller diameter, which takes care of the total loss of excitation, and one bigger diameter circle, which takes care of the under-excited operation near to the stability limit. So again, we have to see that characteristics of the loss of excitation relay should have sufficient margin with the capability curve so that you can operate the machine in a safe manner. So, you know, these are the various coordination methods by which one should ensure that there is no undesirable tripping, even if you operate the machine in under-excited mode. We talked about voltage support responsibility of the generator, especially when the voltage levels are high. If all the generators absorb the reactive power generated by the transmission network, then the over voltages can be controlled. And while doing that, this protection, if they are well coordinated, there won't be any undesirable operation. So this is related to coordination between under-excited relay and the capability curve. We talked about backup impedance relay and its reach. Unbalanced currents. Sometimes not so much for hydro units, but this unbalanced load negative sequence protection is important for thermal machines because there is a negative sequence which is a double frequency component of the current can result into excessive heating. So unbalanced protection is another protection which needs to be properly coordinated, especially when the there is a disturbance in the grid. And there are guidance provided in terms of I squared I2 square T characteristic, which defines the negative sequence capability for different types of. So this is given here. Then we'll come to the main issue related to instability of the network. Yesterday we saw this transient instability phenomena, which is governed by this equation. And we also saw various corrective measures which will act in a manner to increase the power flow capability of the transmission corridor, either by correcting X by, say, series compensation of the lines, X can be reduced. So same line can then transmit more power, or we can put a STATCOM, which will increase the or boost receiving end voltage. And you can also have the angular shift corrected by phase shifting transformer or unified power controller using the flexible AC technology. So basically, by playing with these different parameters, this power flow can be managed. This is the type of waveform the typical waveform seen by the generator when there is a system disturbance, and you can see the power oscillating, right, and voltage and current. You can see this is the current and this is the voltage. Current going right up to 0. So you can see this is actually frequency of the oscillations, what we were talking about. So typically this frequency will be few hertz. When it completes, this one cycle is come to, this is called one pole slip. That means it has gone through one maxima and one minima. So one slip is completed. Then this will be the second pole slip. Then this is a third pole slip, like that. Likewise, there is a number of pole slip which generator can tolerate. Every pole slip results into stress on the generator in terms of mechanical forces. So there is a risk of damaging mechanical components due to torsional stresses, as well as there is a risk of loosening of the winding within the slot due to vibrations. So pole slip is one of the I would say risky or hazardous condition which should be avoided. Normally, if the electrical center is on the generator and transformer side, that means if generator itself is experiencing a pole slip, the thermal machines are tripped at the first pole slip itself. That means in one cycle, this pole slip protection generator will act and isolate the machine. Whereas if the disturbance is beyond generator transformer well into the grid, then maybe the severity on the generator side will not be so high. So you can afford to have more number of slips like this. This is basically done so that the other interventions by way of power swing blocking and power swing out of step tripping on the line protection can correct this situation. So this is typically the picture on the impedance side. What we see here, this is the typical picture on the impedance side. Again, this is a R and X diagram, and for 400 kV lines, it is recommended that the characteristic chosen for distance relay should be a polygonal characteristic. Why a polygonal characteristic is chosen is basically because the x-axis reach, which is basically the line impedance, is independent of the resistive reach of the distance relay. These can be set independently. So that is the advantage of the this characteristic. Advantage from the fault perspective is also that high resistance faults, which are often experienced, can be better sensed by this characteristic because you have got a better resistive reach. Unlike in the circular characteristic, where the resistive reach is decided by the diameter of the circle, which is basically the reactance of the line. So reactance decide the resistive reach. So there is a limitation on the high impedance or high resistance fault detection. So polygonal characteristic is preferred. In the polygonal characteristic, if you see the power swing phenomena, now this power swing phenomena, if it is a stable swing, what we mean by stable swing is swing will result into the impedance moving into the distance relay characteristic, but it will move out. So this is a stable swing. So one or two swings will take place and system will become stable. But if the swing is a unstable swing, that means it is not recovering back. In that case, the impedance will continue to move and it will continue to move towards left-hand side. And that means the negative R side and exit the characteristics. And in that case, this is a unstable swing, and it is then recommended that we should then trip the line or generator on post-slip protection or out-of-step protection. So this is the difference between power swing which is stable and power swing which is unstable. Now, there is a question whether post-slip protection is needed really for all the types of generator, because the ability of the generator or capability of the generator to withstand asynchronous operation varies. One of the parameters which govern this is again the short circuit ratio, which we discussed yesterday. The short circuit ratio for the thermal machine, which is less than 0.5, obviously means that its ability to withstand short circuits as well as asynchronous operation will be limited. Hydro generators which have a short circuit ratio of close to 1 or even more than 1, they are more robust, they are bigger in size, and they have better ability to withstand electromechanical forces created due to post-slip condition. So many of the hydro generating station, you may not have post-slip protection. All thermal machines of say 250 megawatt and above, it is mandated post-slip protection. Hydro machines for 100 megawatt and above, again it is now mandated. But the risk to hydropower station on account of post-slip is much less because chances of severe unstable power swing experienced by the hydro generator because of its moment of inertia and mass, etc., are much lesser as compared to the thermal power station. So many of your stations maybe perhaps are without post-slip protection. Anyone want to give feedback on, do you have post-slip protection on your powerhouses and your NHPC plants? Anyone would like to share? Are you able to hear?
We have, sir, in Parvati stage 3.
What is the capacity of the generator?
130 megawatt each unit.
Okay, yeah. So 100 megawatt and above, generally it is provided. That is
yes,
the CA's technical standard. So as per that, it must have been provided. Yes. Any station in NHPC of say 100 megawatt and more, which doesn't have post-slip protection? Okay, so we assume that it's there in most protection. Now, pole slip protection is similar phenomena is experienced on the transmission line side, and we'll look at the phenomena. We already some of these slides we are already I have explained to you regarding this pole slip phenomena on the generators and generator transformer and the grid side. So this is basically the impedance line on which pole slip characteristic is based, circular characteristic, and this is the sort of pole slip detection swing which is distinguishing between the pole slip which is within the generator and generator transformer, or it is beyond the generator transformer. So this line is a dividing line. Now, if you see the power swing seen by the transmission line, one of the practice which is prevailing is we block zone 2 and zone 3 except zone 1. Now, this is the philosophy which perhaps is still existing at some of the station. The problem with this is, as I explained, that if you block distance relay operation for zone 2 and zone 3 and allow the tripping in zone 1, there are two major disadvantages. One is that you lose the line, so you weaken the network further. So the chances of instability will further go up, and then the cascade tripping effect will result into a complete grid collapse. So that is the risk. But one of the assumptions for this practice is if the power swing goes through zone 1, it means it's a unstable swing, and it is better to trip in that case. So that was the philosophy so far. Second aspect is when the power swing is taking place, and if these are your say detection blinders, normally there are blinders in the distance relay for detection of power swing. So there are double blinder scheme. The double blinder scheme basically when the impedance starts moving the power swing gets detected. Their blinder, time taken from crossing first blinder to second blinder is a criteria to decide whether this is a power swing phenomena or there is a fault. Because when the fault takes place, then also the impedance swing happens, and it should not happen that protection is blocked when the actually fault is there. So this basically is able to power swing due to impedance swing due to power swing phenomena versus the impedance fault phenomena. So that is another feature. Second is when this swing further continues and goes.
Your voice is breaking, sir.
Yeah, there was a, I think, system network internet issue, but that alarm got reset, Am I audible now? Well, it was there for a very short time.
Yes,
sir, audible.
yes,
Yes, sir.
okay.
You are audible.
Yeah. So when the impedance locus actually comes to zone 1, actually the electrically, the power swing wise, you are almost 180-degree apart between the system and the generator. So if you allow tripping to take place in zone 1, you are actually risking opening of the breaker when the two voltages which are swinging are actually in opposition, thereby chances of restrikes and pole failure will become more. So there is a actually greater risk of breaker failure when the opening of the breaker is done in zone 1 during the power swing detected condition. So the second option is block all the zones and trip with out of step function. So this was the recommendation given after the 2012 grid collapse, that you should not block only zone 2 and zone 3, but block all the zones, and then there is a separate out of step protection function in the now modern distance relays. You use this function either to trip this line which is being protected, or system by mode tripping. So this out of step function is one of the methods of, you can say, controlled isolation of an area or a power station in a manner so that there is a generating station survival along with some load. So it's like a controlled separation strategy. So this is what is recommended. But where to apply out of step protection, this is something which requires some careful study. So till now, since 2012, I think out of step application for tripping, at least I am not aware whether it has been really applied in our system, but this has been the recommendation after this. In the northern region, actually, Regional Power Committee of Northern Region, they have already given instructions to adopt blocking of all the zones and tripping of the same line by out of step protection. So this has been already done partly. Other regions, I'm not aware of this thing, but this is the recommendation, general recommendation. The second thing about how do we ensure that lines do not trip in an undesirable manner during power swing or load swing phenomena. The second issue is the load encroachment phenomena. The load impedance encroachment is a significant risk, as we said, due to phenomena like voltage instability or voltage collapse phenomena, which I had explained with the PV curve. And what happens is, if this is your, say, circular characteristics of the distance relay, then during this power swing condition or the load short time emergency loading condition due to, say, voltage collapse phenomena during dynamic instability, the load on the line will become so high that it will cross the zone 3 characteristic of the distance relay, and then the tripping will occur. Now, in this case, the relay is not able to distinguish between the load causing encroachment into the impedance characteristic or whether it's a three-phase fault. Because as far as the relay is concerned, relay sees it as a three-phase fault. This is the load swing. Now, during 2012 grid collapse, some of the protection, distance relay protection, did not have this load encroachment prevention feature. So the lines, number of lines tripped on this load encroachment, giving the indication of zone 3 three-phase fault. As a mitigation of this, there is a now feature which has a load encroachment blinder characteristics. So this blue zone, actually you can see is a load encroachment blinder characteristics, and as the load encroaches into the impedance circle of the zone 3, still the tripping is prevented because of this load encroachment characteristic. So in this zone, the tripping is prevented. Now you can see this zone actually it is very close to the R axis. That means it is purely seeing only the loading phenomena, high overload phenomena, and not susceptible for the fault phenomena. Because when the fault takes place, the angle is likely to be very much reactive. That means more almost 90 degree, and usually the impedance point will be closer to X axis and not closer to R axis. The impedance due to load will be closer to R axis, whereas impedance due to fault will be closer to the X axis. So that is the distinction relay makes between load encroachment versus the fault condition. If you see the polygonal characteristics, then similarly in the polygonal characteristic also, you can see there is a load encroachment feature where this characteristic can be set, where even if the load point enters this zone, the tripping is prevented. So this is the second major recommendation, or I would say third recommendation. First recommendation being that all the distance relays at 400 lines should preferably be with the polygonal characteristic. Second is power swing blocking philosophy should be changed. Instead of blocking only zone 2 and zone 3, all three zones should be blocked during power swing. But the tripping with out of step criteria should be implemented. And third is load encroachment characteristic should be activated so that during dynamic overload condition, tripping due to load encroachment can be prevented. Now the question here is how much overload we permit of the line. Rating criteria which has been given is basically 150% of the emergency loading condition. So 150% overload for 15 minutes is permitted on the basis of conductor capability, and this is termed as the emergency loading capability of the line. Either this or the maximum loading capability of the current transformer or the isolators of the line, or whichever is the lowest, that should be the criteria. Usually isolators which will have much higher current carrying overload capability compared to the transmission line conductor, or even the current transformers, the overload capability may be better. So basically the thermal rating of the line into 150% accompanied by voltage, low voltage conditions to the extent of 85%. So that is the criteria which has been recommended for which the tripping should not occur. 150% overload of the conductor accompanied by 85% under voltage condition. So that for that the tripping has to be prevented. So that is basically the recommendation which is given in this slide. Next protection which again gets affected during grid disturbance is overfluxing protection. This overfluxing protection either can be during the system disturbance, unstable operation, or it is after isolation when the region gets isolated. Again, depending on whether you are importing the reactive power from other region or you are exporting. If you are exporting reactive power and isolation takes place, then you will have excess reactive power resulting into over voltage, and overfluxing condition can happen. So this is one of the risk during system disturbance condition when isolation takes place for any area, and if the area happens to be exporting reactive power after disconnection, this area may experience over voltage condition. Opposite to this is if the one particular area is importing reactive power from other region and the disconnection takes place, then this region will be in short supply of reactive power, and then there will be under voltage condition. So these are the, but for the purpose of overfluxing condition, it is basically over voltage, and sometimes over voltage condition may be followed by under frequency condition. As the grid cascade tripping occurs and power swing takes place, along with the voltage instability, there could be angular instability resulting into frequency getting unstable, and then there will be if the load shedding measures and other under frequency protections, dF by dt protections do not cause adequate load shedding, then there will be under frequency situation. So this overfluxing protection basically is a V by F, and this higher voltage accompanied by lower frequency can cause then tripping of the transformers, especially interconnection transformers and generator transformer. Both are susceptible for tripping on overfluxing, and in many disturbances we have experienced that overfluxing protection operates in an undesirable manner. Similarly, the coordination of over voltage protection of the line. Now, when this normally the over voltage protection is set at 110% with some time delay, and for extreme over voltages to the tune of 130% or so, the time instantaneous tripping has been provided. So there is a two-stage over voltage protection, and this over voltage protection again, as I explained, can be one of the protection causing undesirable tripping due to over voltages taking place due to mismatch of reactive power demand and the reactive power supply. Face over voltages, and you may lose the lines due to over voltage protection. Now here again, some coordination is required, or the setting change in an automatic manner should happen if you are isolated. If you are islanded condition, then maybe the time delay should be appropriately higher, so that corrective actions for over voltage by way of switching of reactor or backing down the or absorbing the excitation reactive power by the generator, these actions can bring down the voltage. So this is something which needs to be again. Again, I'm giving you here 3 good references which you can read. There are 2 SIGRE reports. One is optimization of the protection performance during system disturbance, and there is also a report on protection against voltage collapse. For the hydro machines. There is a good SIGRE report also on synchronous generator, abnormal operation, and special protection and instrumentation systems. This report, working group report, is also available, which you can refer to for more information on protection control aspects. So with this, we will stop here on this fourth session. We will open now session for the general question and answer on any one of the 4 sessions yesterday and today, as well as any questions related to the quiz which you took in the yesterday morning. So we'll spend 10-15 minutes on the discussion. Open to you. Any questions?
सर नमस्कार सर।
नमस्कार
सर इसमें सर कैन यू able to see the slide I have shared? कैपेबिलिटी जनरेटर कैपेबिलिटी कर्व जो है एक मैंने शेयर किया है सर। आप
यस
देख पा रहे हैं?
हाँ
सर इसमें एक इधर ओवर एक्साइटेशन में लिखा है फील्ड हीटिंग लिमिट लिखा है और अंडर एक्साइटेशन में स्टेटर हीटिंग लिमिट है सर। इसका मतलब ये अंडर एक्साइटेशन में क्या स्टेटर हीटिंग लिमिट कैसे आ रहा है और ये ओवर एक्साइटेशन में फील्ड हीटिंग लिमिट मतलब इंटरनली क्या व्हाट इज हैपनिंग कैसे हो रहा है आप बता सकते हैं, समझ सकते हैं इस बेसिस पे?
In the over excitation region, basically there is a depending on the capacity of the exciter का current limit and the generator stator का भी current limit, they come into the picture. Whereas in the under excited mode में there is a stator overheating due to excessive leakage flux in the end region of the generator. So there is a end region overheating the generator during under excited operation. So these two are different type of phenomena. So one is related to the excessive leakage flux and in the under excited mode, whereas over excitation mode mein it is a thermal limit of the current carrying capacity of the exciter winding and also the generator stator winding. So these two on part of the capability curve, under excited and over excited, are related. They are independent of phenomena is different.
Sir, in over exertion, flux is more than the required. That's why field winding, I think.
Flux is not more than required. The field current which is supplied to generate required reactive power within capability curve. There is a limit. So, but it is still within the capability curve. Till you hit the ceiling of the characteristic where the over excitation limiter will prevent you to increase the field current further. So if you are operating the excitation system on manual mode, you can still refer to the capability chart so that you don't exceed the field current limit on the exciter to take care of its thermal capability. In the under-excited mode also, the characteristic is more limited by the overheating in the end region rather than the current limit, because you are actually absorbing the reactive power from the grid. So there is a reduced requirement of the field current in the under-excited mode, because you are drawing excitation from the grid, thereby taking reactive power from the grid. So you are absorbing actually the reactive power from the grid. So the limitation comes more on the because of the overheating rather than the current limit.
Okay, sir, under excitation, as per my knowledge is concerned, under excitation means already it is field current is less than the required flux, no, sir? So where how it is happening, stator heating limit.
No, field current is not. See, air gap flux will remain as required, but it is partly the air gap flux is given by the reactive power taken from the grid and in under-excited mode. So what the air gap flux is a mixture of flux density produced by the field winding and the excitation drawn from the grid. So it's a combination of that. That's why there is a overheating, because you are drawing excitation from the reactive power from the grid. So there is a overheating of the teeth in the end region, and this limitation comes out of that. It's not that the air gap flux requirement is come down, but the way air gap flux is managed, that is different in under-excited mode. Whereas in over-excitation mode, you are actually supplying reactive power. So entire air gap flux is produced by the field current. That's why the field current value will be high. So in the over-excited mode, because you are not drawing any excitation from the grid, you are actually supplying reactive power to the grid.
So that means in under excitation mode, stator heating limit means stator core heating limit, no, sir? This one? Yes,
yes. In under excitation mode, the heating is limitation comes first. In over excitation mode, is the excitation winding heating becomes a limitation.
So, sir, according to this curve, so how can at what range I can operate the machine?
That is what is given in this x and y axis, no? So within this curve, you can at any point as it is required for the grid within the capability curve for MW as well as MVR. Within this capability, at any point you can operate. As I was mentioning, when sometimes when the grid condition is critical, you need to give voltage support to the grid by more reactive power, and in that case you may have to back down active power so that more reactive power can be supplied. So within this capability curve, you can operate at any point within the capability curve.
Okay. Thank you.
Any doubts or clarification from the quiz questions?
Sir, can you share the answer key of the questions?
No, answer key will not be shared. If you have doubt on some questions, we can clarify that. Answer key is only for evaluation of your answers. But if any doubts are there, we can definitely respond to that. because the same quiz will be given to you again at the end of the program. It's your understanding that, which is more important.
सर ये इनरश करंट के बारे में थोड़ा बता दीजिए ट्रांसफार्मर में.
Yeah, transformer, when you energize, it's not applicable to generator transformer, because generator transformer you normally build up the voltage gradually. So there is no inrush phenomena for generator transformer. But for the power transformers in the grid, when you switch on the transformer at the depending on at the point of supply on the waveform, whether you are at the near to the zero crossing or near to the peak, the inrush current will take place because of the magnetization requirement of the core. As you know, the core has a certain magnetization characteristics. As the flux will build into the magnetization, initially the current drawn will be very high, and this current magnitude can be 6 to 8 times the normal full load current in terms of peak magnitude. But the waveform wise, the inrush current is not a sinusoidal waveform. It has got a primarily a very high second harmonic. It's a peaky waveform. I will not be able to share that slide just now. Normally we cover that in a protection program. So this inrush current, which is seen only on HT side of the transformer from which you energize the transformer, can cause differential relay to operate and trip the transformer. So to prevent that tripping, basically the second harmonic component of the current is basically taken as a restraining current, and the differential relay operation is prevented by providing a restraint in operation by the magnitude of second harmonic content. Now, usually the setting of inrush current second harmonic content is around 18%. Some of the newer type of magnetic cores, the second harmonic content can be lower than that. So settings up to 15% are also available and can be adopted. Very low setting is also not advisable because it will become difficult for relay to distinguish between the fault, because fault current also contains harmonics, including second harmonic. And when the transformer fault takes place, you should not be preventing relay operation. So relay should not get blocked during fault condition. So these are the two contradictory requirements, that on one hand you want transformer definitely to trip when the fault is there. At the same time, you don't want transformer to trip when there is a inrush current during charging. So inrush current setting is optimal around 15% second harmonic to block the operation. And modern numerical relays has got a further features by providing the cross blocking feature phase wise. Older relays had a average setting of inrush current second harmonic content. Now instead of average of 3 phases, and each phase depending on the instant of breaker closing will draw different second harmonic, different amount of second harmonic. So these deficiencies of older relays are overcome in numerical relays by providing the phase wise measurement, and even if one phase gets high second harmonic, other 2 phases are also blocked. So this is called a cross-blocking feature. This also prevents maloperation of the differential relay during overexcited condition, overfluxing condition, where there is a high fifth harmonic. So this is basically the background on inrush current and harmonic data.
Thank you, sir.
Yeah. Yeah, any more question or we can close for the day? Lambaji?
सर थोड़ा ऑटो रिक्लोजर के बारे में बता दीजिए सर थोड़ा, एक क्वेश्चन इससे रिलेटेड था ना सर पहले.
हाँ, auto reclosure basically in our single phase auto reclosure is opted for 400 kV line to help transient stability. That means in order to maintain the transient stability, the single phase auto reclosure is recommended. And I had explained the reason why single phase auto reclosure, because during the short circuit faults, either phase to phase or phase to ground fault, the amount of active power which will drop due to voltage dip can be minimized. By minimizing the active power drop during fault condition, you are actually reducing the accelerating power between the prime mover turbine and the generator. Because when the electrical fault takes place, the active power will get reduced because of the dip in voltage, but the turbine will continue to produce the same amount of mechanical input. So there is a mismatch, and then the acceleration will take place. So to prevent this accelerating power to be excessive, single phase auto reclosure is utilized, so that at least on the other two phases power can continue to flow. So the delta P, which is the accelerating power, is minimized. That is basically the concept behind single phase auto reclosure.
थैंक यू सर.
कल के क्विज में किसी को कोई प्रॉब्लम नहीं है? In that case, if there is no question, no clarification, we can close the session. Participants, किसी की clarification नहीं है कोई?
सर ये क्वेश्चन नंबर 9 में 2 आंसर्स करेक्ट लग रहा था वो, लेकिन एक ही सेलेक्ट हो रहा था.
क्वेश्चन को पढ़िए ना उसको.
Which of the following statements are true? The reactive power produced by the line capacitance is equal to the reactive power consumed by the line inductance is called natural loading or surge impedance loading, SIL. And the other one, at the heavy load condition, the third option is also right? At the heavy load condition, transmission lines consume reactive power and decreasing the line voltage, and in the low load condition generate increasing line load voltage.
आपके पास क्वेश्चन है पटकी साहब?
क्या मैं समझ गया क्वेश्चन. I think इसमें, as I recollect, all the statements are true actually, as you are saying. Yes. All the three statements are true in this case. So your answer should be all the statements are true.
But there is no option for all the statements. Actually.
No, it is only saying which are the statement which is true. That is the question, no?
Then if all the statements are true, then option should be there to select all the three. But it was not like that.
Which of the following statements are true? So all the three statements are there. So you can just write that instead of A plus B or B plus C, you just say all A, B, C are true. You can just write there like that. That is what is expected. It's not a tick mark. You have to just say which statements are true. So you can either tick on A, B, C. That means all are true. Or tick only A and B. Then only A and B is true. Understood?
Okay, but there is no such option for writing also.
You can take all the three.
You can
take all the three.
When you select the other one, the first one will be removed and select the second one.
No. Whichever statement you feel is true, you just tick that. Put a tick mark on that. So if all
at a time only one is selecting.
No. In this case, that is not true. There are some questions where more than one answer is correct.
But actually, one is selecting at a time.
Okay, that option we will see. We will see that option if it is not being ticked all the three at a time. That we will see.
No, let it be clarified, Lambaji. Tomorrow also you can clarify that it's not necessary that only one answer is correct. It's quite possible that more than one answer is correct.
Okay.
So in that case, you should, if you feel that two answers are correct, you tick on both.
Sir, there is one more request.
Yeah.
Sir, there is one more request. The first day quiz, we can have a small session for discussion over that quiz. About 10-15 minutes, we can discuss over that. So what is for all the questions?
I think during our deliberations of the sessions yesterday and today, all the questions have been covered in my discussion. If you have been attentive, you will see that all the questions have been answered.
Sir, we are attentive, but the problem is here that most of the locations are in a very remote place, and networks are frequently coming and going, and most of the time voices are cracking, and so we miss some of the important part. That's why I am asking this and requesting.
You should not be problem in all the question, na? That's why we are telling that if any clarification in any question is required, that you can ask. Not all the questions. You must be having some problem in 1 or 2 or 3, 4 questions, na? No, not all 15.
Yes, sir, that is true.
So you can get it clarified now. Wherever you have doubt, you can get it clarified now.
At the moment, I don't have that list of questions, so I will try to do it by tomorrow.
Okay.
Thank you.
Sir, regarding block starting.
Yes.
Sir, RLDC, how it will decide which power station will do the block starting exercise, mock test, and what parameter it will decide to block starting purpose, and if my power station will selected for block starting, so what parameters can I do? Can I change regarding this? Can you explain, sir, briefly?
Yes, basically is black starting selection primarily goes with the ability of the power station to have black start facility, and some of those necessary conditions which are required in terms of
आपकी आवाज
control.
थोड़ी सी प्रॉब्लम हो रही है सर, आवाज ठीक नहीं आ रही आपकी।
नहीं क्लियर है अभी।
Okay.
Voice clear
my side the network looks good. There is no yeah. So basically first choice is the ability of the station to deal with black start condition. All the necessary control modifications etc. should be available. Second is the purpose of black starting is to normally provide startup power to the thermal power plant. So the load dispatch center will identify which is the power station which will be in need of black startup power. So how to provide that startup power to the power plant? So they will identify the nearest hydro power plant and availability of the dedicated corridor to supply that startup power to the station. So based on the available network, again the load dispatch center will see how the lines can be lined up right up to the power station so that startup power can be provided to the power station. So these are the basically three criteria. That means the hydro power plant should have necessary ability to do the black start. The second is the transmission line corridor should be available on a dedicated basis to supply startup power to identified power station, based on which this thing is decided.
So what is the control modification, sir? Is there any?
Yeah, we say as we explained that the governor control as well as the excitation control modes need to have certain provisions so that line charging, for example, you should be able to close the breaker on dead bus. You should be able to then slowly build up excitation on manual mode. You should be able to control the voltage at the open end, at the remote end, so that over voltage should not occur. So maybe the reactor should be available to be switched in. So likewise, for different types of likely contingencies, what are the control actions required? Availability of that will be checked, and depending on that, choice is made. Which are the power stations which can provide a startup power to which thermal power plant? That is basically the study. And of course, it's not unilaterally decided by load dispatch center. In the regional power committee, normally there will be a discussion on all the aspect of black start, and after all the requirements are met, they can declare that this is the power station which will take startup power from this particular hydropower station, and this is the corridor which will be required on a dedicated basis. When we say dedicated basis, means there should not be any other hanging load on that, which is of critical nature on that corridor. So you should be able to line up that corridor and do the line charging. Yeah. Also, it depends on the length of the transmission line which needs to be charged, so that there is no capacity over voltages taking place. So all this study is required to be done before declaring black start mode of operation for a particular power plant.
Okay.
Then thank you participants for the day 2 sessions, and all the 2 sessions of today has been completed now, and 1-day training program is still there, and tomorrow Mr. Kamin Dawai will be the faculty, and the topic on fault analysis. So be with us at 10:30 for these 2 days. I am thankful, very much thankful to Patki Sahab that he has very nicely explained each and everything and clarified all the queries of participants. And I think that it was very, very beneficial for all the participants also. And tomorrow's session will also be very interesting regarding the fault analysis. And Mr. Kamin Dave is also very, very experienced person. And number of persons you must be knowing him also and must have attended his sessions previous also. So thank you very much, participants, all the participants, and thank you for your participations. And thank you, Patki Saab, for your nice presentations. Thanks a lot, sir.
Thank you.
Okay.
Thank you very much. Thank you all.
Okay, sir. Thank you, sir. Thank you.
Thank you, sir. Thank
Thank
you.
you, sir.
Be with us
Thank
at 10:30 sharp tomorrow.
Okay, sir.
Okay, sir. Okay. Thank you, sir.
Thanks a lot.
Okay, I will log off. Thank you.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.